Hi guys, the next video is looking at a new chapter. This video is looking at the exponential and logarithmic functions. So this is part of our Year 12 Advanced Mathematics course, and we're looking at chapter 5. And so the chapter is going to start off with exponentials and move on to logarithms. Now we've worked through a lot of this in our Year 11 maths course. So the first couple of exercises that we worked through, which will be 5A and 5B, and fairly large amount of 5C stuff that mostly we've done before, so I won't be dealing too much with that, and the videos will be slightly smaller for this. So the first one, review of the exponential function base e. So exponential functions are those in the form of y equals k to the x, or some value or constant called k, and we've got an x raised to the power. We previously defined the exponential function to be that which is represented by this formula here. So y equals e to the x, where e is a number, e is an irrational number, and e is this number here, 2.7183, and it keeps continuing on. It has the property, e, of producing a tangent line at the y-intercept of gradient 1. So if we were to draw this graph of y equals e to the x, it's going to cut our y-axis at the point 0, 1, and it's going to take on this shape. And you need to know that general shape of what that's going to do. There's going to be an asymptote along the x-axis here. That's going to act as an asymptote, so our graph will never actually touch that, and our graph will continue up here. So if we were to draw a tangent at the curve at the point 1, it would have a value of 1. The gradient would be 1. So that's a good definition of the curve. So that is a revision from Year 11. In this case, if we're looking at the domain, so we'd have a domain of all x values, but our y values would be only, as our range, be values of y greater than 0, because the x-axis is an asymptote. The function is 1 to 1, and remembering when we differentiated e to the x, we still got e to the x, but we'll have a look at that in the next couple of exercises as well. We had these definitions as well. If we jump back to the HSC formula sheet, I'll do that now just to remind you of what was in the HSC formula sheet so that you know what you need to know. So we are given this, okay, that log of base a of a to the x is equal to x, so that x basically coming down. It is also equal to a log of a to the x, and we're given these two as well. I'll change the base formulas, and we're given this as well. So they're formulas that we're given. Anything else, logarithmic wise, we need to remember. So let's just jump back into exponentials and logarithms. So this one we're given, this one we're given. So we don't need to memorize those. So just looking at transformations and dilations of our curve, we can apply the ones that we learned in Year 11 to the exponential function. So here's our basic e to the x curve. It's going through the point 0, 1. If we were to change our e to the x to e to the x minus 2, so x is going to be going to x minus 2, so our graph is basically shifting towards the right 2 units. Translating our graph so it becomes e to the x plus some constant would mean that we're moving our whole graph up, so this graph would be shuffled up. Likewise, if that was a minus some constant, our graph would be shuffled back down. So they're Year 11 concepts. You just do a little change on your diagrams you've got in your booklets because they're a little bit incorrect. But if we were making our e to the x become e to the 3x, then what we are going to be happening, if you think of what happened in Year 11, x would be going to x divided by a third, and that would give us our 3x. So our dilation factor would be 1/3. If we remember back to Year 11, I was writing that like x would be going to x divided by 1/3, which gives us 3x. So that's where that 3x is coming from. So our dilation would be 1/3. Similarly, but looking at it the other way, if our graph was going to be coming from y equals e to the x to y equals 3e to the x, what is happening is I would probably be writing that as y over 3 equals e to the x. So y is being changed by a factor of 3. So y would be going to y over 3. So our dilation would be 3 in the y direction. So we'd be moving our graph up here to 3. The other one that we looked at in year 11 was a reflection in the y-axis, and that was the same as x going to minus x, or x would be going to x over minus 1. So we've got a minus 1 dilation for x, and that means x's were over here in the positive direction. Now the x's are flicked over, and we've kind of popped them in that way. So the graph changes directions, and that one is called a reflection in the y-axis, and that's what happens when x goes to minus x. Okay, so positive x's become negative x, so they're reflecting themselves in that y-axis. These things here are year 11. Okay, so if you're finding that that's something that you're not quite familiar with, you need to go back and have a little bit of a look, because that's what the chapter's going to have a look at, is those kinds of things. Okay, it's also going to have a look at finding tangents and normals to curves. And again, that was stuff that we did in year 11. So let's just see what we can do with this question here. The example is saying, let A be a point on the curve, y equals 2 times e to the x, where x is 1. We want to find the equations of the tangents and the normal at point A. Okay, so we need to think about what that actually means. When we were finding tangents and normals, as soon as you think of tangent, you need to know, and looking at equations, we need to think of the gradient. And what did we do to find the gradient of the tangent? That was our first derivative. Okay, so y dash will give us our first derivative, which is going to be 2e to the x. Remembering that when we differentiated e to the x, we still got e to the x. Okay, so we want to find the equations of the tangent to the normal where x is equal to 1. So in this case, at x equals 1, y dash is going to be equal to 2 e to the 1, which is just 2e. So what we also know is when we have our point x being equal to 1, our y value is going to be equal to 2e to the 1. So that's the point that we're looking at, our x and our y point. So this thing here, this y dash, is our gradient of the tangent. And remembering our normal was 90 degrees or perpendicular to our tangent. So our normal, or our gradient of the normal, would mean that we'd have our 2e, our gradient of the tangent, times by our gradient of the normal, and that would be equal to minus 1. So our gradient of the normal is going to be minus 1 over 2e. Okay, so now that we have our gradient of the tangent, and we also have our gradient of the normal, we can find our equations of both of those. So our equation formula we're going to use is y minus y1 equals mx minus x1. Not on your HSC formula sheet, guys. You need to memorize that one and know that when we're looking for an equation, that's what we're going to do. So the equation of our tangent is going to be y minus, this is happening at this point, 1, 2e. So y minus 2e is going to be equal to, our gradient of the tangent is 2e, x minus our x value. Let's just neaten it up a little bit. So y minus 2e is equal to 2ex minus 2e. Let's add 2e to both sides. So y is going to be 2ex minus 2e plus 2e. So y is going to be equal to 2ex. Okay, similarly, we can find our equation of the normal using the same formula. Y minus y1 is equal to m. The m is going to change. That was 1 minus 1 over 2e. X minus 1. We can neaten that one up a little bit. In doing so, I might just times both sides by 2e. So I'm going to get 2ey minus 4e squared. It's going to be equal to minus x plus 1. And we can lay that in any form that we like. And I might just leave mine like that. We could rearrange it, neaten it up, get x on one side, y on the other, but I'm going to leave it just like that. Okay, that is sort of giving us enough information to work through 5A. So go and have a go at the exercises. Try and go back and have a look at year 11 stuff if you're a little bit stuck with some of the translations and dilations.